Hey, good morning, guys. Today we're going to start a new lesson. Uh, Still on the topic of statistics, but we're going to be looking at uh, inferences, how to make inferences. And so to break that down is basically what conclusions can we make based on the data that we obtained. And since statistics is dealing with, collecting data and analyzing that data, after we've analyzed it, we want to figure out um, is this data significant, or is it just you know is it just a random occurrence that happens every now and then? And so this is why this topic is called tests of significance. uh, if it's something that is significant, then it shows that there is some sort of uh, major change from the randomness that we selected the sample from. Okay, and I'll explain more about significance as we jump into these topics. And then I also want to express the handout that I put on Blackboard um, has 3 pages, right? The last page is the actual assignment. Uh, the second page is a two half-page copy, and so I'm going to be going over that in this video. And then the first page is another kind of a practice worksheet. And so the first 2 pages are kind of a practice worksheet that I usually work in class with you guys to kind of get you, introduced to the steps that we're going to be taking. And I'm also going to be talking about an acronym that we're going to use. Just like how we had an acronym for confidence intervals, that acronym was PANIC. For this topic, for tests of significance, we're going to use an acronym called PHANTOMS, like Phantom of the Opera. Okay, and these are just mnemonic devices to help us remember the steps that we need to take. Okay, and so if you have your handout in front of you, or handouts, this would be the first page that you see on your handout. Okay, and it says scenario 1. Let's go ahead and go through this. It says an income tax service claims that their clients receive an average of $1,000 refund, tax refund. Let sigma equal $125. That's the standard deviation. And refunds are normally distributed. Okay. So, a couple of things. These key points that they made, the fact that they're giving us sigma and it's normally distributed, should alert you that we're going to use, maybe be able to use the z-table. And most likely we are going to be able to use it because they gave us sigma and they explicitly told us that the data is normal. Okay. All right. A local consumer advocate group believes that their average is lower. So they take a random sample of 25 clients and find that the average of this sample is $979. Okay, so what's going on here, right? That's the question, right? So we have a income tax service, okay? So this can be, H&R Block. This can be a friend that you know or someone that's kind of charging you to do your taxes. Maybe your parents go to H&R Block. Maybe they ask a friend of theirs. But however method you choose, right, sometimes they ask for a fee. And so this tax service is trying to appeal to customers and say, on average, our clients receive $1,000 refund. So that's their claim. That's their way to entice their customers, their clients, right? And so a local consumer advocate group, so this is a group that advocates for local consumers, meaning that it fights for the local consumer in case they're getting tricked into something, right? So they want to put this claim to the test. Because this advocate group believes that the average is actually lower. Okay. So if you get a tax refund, do you want a larger tax refund or a smaller one, right? Most of us would want more money back. So they're concerned that it's lower than they say, which means, you know, in a way they're kind of lying to the clients, right? So first of all, let's define the variable. Remember, we've worked with averages and proportions. So again, for this new topic, we're going to still work with averages and proportions. So are we dealing with averages here or proportions? And yet you would say, yeah, we're dealing with averages. Okay, so I'm going to say my variable is this mu, the average, and we're interested in the true average tax refund. Is it truly 1,000 like the company says, or is it lower like the advocate group believes? Okay. Now for this topic, I like to talk about the justice system, because we have a justice system in the US that we say people are innocent until proven guilty. So what does this mean in the sense of the scenario that we're saying? We're saying, okay, we're going to choose to believe that the company is saying the truth. Okay, we're gonna be naive in a way, right? We're gonna say, okay, I believe the company. You know, if they say I'm gonna get an average of $1,000 back, then I'm gonna hold to their claim. So, what do we believe? I'm gonna put we believe that the average tax refund is 1,000. What does the consumer advocate group want to test? What do they want to test for? And it says here, right, they want to test if it's actually lower. Lower. Okay. So we have a parameter of interest. We're interested in the average tax refund. We have a hypothesis per se. We say that we believe that the average tax refund is 1,000 based on the company's claim. And what we want to test is if this claim is true. Now, do we want to test if this claim is larger than they say or lower? So we want to test if it's lower. And again, in order to make a decision, in order to say that we either, this space here, we'd say we either believe or we fail to believe the claim of the tax service. Okay, and so we need proof for that. We need proof for that. So there's two ways actually to get proof. One way is going back to the topic before confidence intervals. We talked about sampling distributions. And since we sampled 25 people, right, it says that they sampled 25 clients, we can get a probability. Okay, so I'm going to go over some symbols that we might have seen before. And if you guys remember this symbol, is the average. We believe that the average is 1,000. And the standard deviation is sigma over the square root of n which sigma is 125 over the square root of 25, and this equals to 25. Okay. So that being the case, if you remember, we would draw a sampling distribution, and we would say, 1,000 is right here. Then we subtract standard deviation. So what's 1,000 minus 25? $975, right? 1,000 minus 25 again is 950, and then 925. And I can go up to 1,025, 1,050, 1,075. Now, I'm not going to ask you to draw this every time, but I just want to go over it again so that we remember doing this, right? And we also know that from the sample that we got, what was the average tax return? I think it was $979. So do we agree that 979 is maybe about here? This red mark is where 979 is. And how much shaded, or are we interested in lower than 979 or higher? We're interested in lower. So we're going to shade all this here, right? And so how do we figure out, going back to sampling distributions, how do we figure out what that value is? And so if you guys remember, we had to find a z-value, which the formula for that was the following. And so if I plug in my values, I get 979 minus 1,000 over, what's this value? It's in it, the one we calculated here, it's 25, right? So divided by 25 gives me a z-value of negative 0.84. Then we would go to the z-table, right? So let me go ahead and pull that out. And we're looking for negative 0.84. So that would be, let me zoom this out a little bit. Okay, so negative 0.84. So I see that negative 0.8, let me use a different color. Let me use purple. Negative 0.8 is there, and 4 is up here. And so where do these meet? What probability do they meet at? So can we zoom in? Yeah, it's 0.2005. 0.2005. Because remember, just want to remind you guys that the z-table shades everything below, and remember we're shading everything below 979. Okay, so we're going to move this out of the picture and put it down here. All right, so we're going to say that the probability that the average is less than 979 is, from the z-table, we got 0.2005. Okay, and so that's 20% chance. We got a 20% chance that the tax refund is lower than 979. Now, the question is 20 very likely or unlikely? You know, how far was 979? How far was 979 from the mean? Was it exceedingly far, like 3 steps away, or no farther than 1 step away, right? So this is what we're looking at now in this topic is our result significant or not? When they sampled these 25 clients and they got an average tax return of 979, was this, you know, significantly small, or was it common? Was the chances of this happening very small or very large? Was it uncommon or very common? Okay, and so based on what we got for the probability, we got 20%. I would say it's pretty common, because remember it says an average tax return of $1,000, so that can be plus or minus 1,000, so it can be slightly off. Okay, so my conclusion is going to be here. I'm coming back to this point here. What decision are we going to make? Are we going to believe the claim of the tax service because of the proof that we got, or are we going to fail to believe it? And I'm going to say we're going to believe it. So I'm going to put the word believe in this space here. We believe the claim of the tax service. So we believe the claim of the tax service because of this. And I know some students are going to ask, before you guys ask, but I know some of you are going to ask, how do we know that 20% is large or small, right? There has to be some sort of percentage that we compare it to. There's some sort of minimum, right? And so, again, we're going to discuss this a little bit later, but there's something called an alpha value that we're going to talk about, and this alpha value represents a level of significance. Okay? Level of significance. And sometimes it's 5%, sometimes it's 3%, sometimes it's 10%. But the default that I like to always use, and most statistics use, is an alpha value of 5%. Meaning that if the percentage that I get is larger than 5%, then it is not a significant event. If it's less than 5%, then it is significant. Okay. If you win the lottery, is it significant? Yes, right? What are the chances of winning the lottery? Are they really big? Is it a really large percentage of chance that you're going to win, or is it a very small percent chance? And that determines the level of significance, right? If it's a very small percent chance, then that is a significant event. Winning the lottery is a significant event. So this event that they did of sampling 25 clients and getting an average tax return of 979 wasn't a significant event. Okay? Now, I want you to try scenario 2. I did put it in the PowerPoint slides, but I want you to try it. I hope the explanation of scenario 1 helps you for scenario 2. So yeah, try it out. Try scenario 2. Oh, and I almost forgot. There's also another way to check it. We can also use confidence intervals. And so I'm going to put an image in here. And so if I use confidence intervals, remember the formula for confidence intervals. It was x bar plus or minus z times standard deviation over square root of n. Okay? And so I went ahead and calculated it here. I did the subtraction and the addition, but the z value that I used corresponds to 95%, which gives me a z-score of 1.96. Okay, so I added and subtracted. Underline. I added and subtracted, and I got a lower bound of 930 and an upper bound of 1028. And what I'm checking for, so what I got in this confidence interval was a lower bound of 930 and an upper bound of 1028. This is my confidence interval. Let's say 95% confidence interval. Okay. And so my question is, what was the company's claim? They said that their clients receive an average of $1,000, right? And so the question is $1,000 in the interval? Is $1,000 in this interval? Yes, right? So then that gives us a conclusion that we can also, again, we could believe the claim of the company. Okay, so we can check it through confidence intervals, but the main way that we're going to use for this method, the main way of checking, is finding the probability. Okay. All right. Okay, so a couple of definitions that I want to look at. Let's go to those. All right, one of the first definitions is a test of significance. It's a method for using sample data to make a decision about a population characteristic. So we compare it to the scenario that we saw with the tax refund. We used the sample data from the 25 people to compare to the claim that the company had, right? From the sample of 25 people, they had an average refund of $979, and we want to compare that to the population claim of $1,000. Okay. The second term that I want to introduce is called the null hypothesis. It's written with the notation of H with a subscript of O. Sometimes in math terms they call it H naught, or you can just call it HO. And for the example that we just did, the claim was $1,000, right? That's what the company is claiming that they can get you if you get your tax refund with them. And then the alternative hypothesis, written as H with the subscript of A, that's the value that we're comparing it to, right? We compared it to 979. So if 979 was the value, is 979, how does it compare to 1,000? Is it more than 1,000 or less than? Okay. And 979 was less than 1,000. Okay. But we want to know, is that 979, is that a common occurrence or is it very rare and significant? Okay. And the last thing I want to mention is that for the alternate hypothesis, you might have the use of less than, greater than, or not equal to. These are possible notations we could use for the alternate hypothesis notation. Okay, so if you continue on your handout, there is a second page, and it's 2 pages. Well, it's 2 parts, sorry. It's 2 half sheets. So you have the same thing on both the top and the bottom. I usually print them out and give you guys half sheets, but this is my master copy, so it has both the top and the bottom part. But we're just going to look at these 3 examples here. So it says, for each of these scenarios, state the null and alternate hypothesis, draw the distribution, calculate the probability. Now, I guess for our case, you don't have to draw the distribution because I have some slides for you, so I'm going to go through those slides in this video too. But I do want you to practice identifying the hypothesis, or hypotheses, because there's 2, right? The null and the alternate, okay? So, first off, let's look at the first example. Chrysler claims their Concorde will go from 0 to 60 in 8 seconds. 0 to 60 miles per hour in 8 seconds with a standard deviation of 1. Okay, so this is given to you. It's kind of given to you in the background, right, of the problem. Consumer Reports stated that the mean time for their sample of 10 Chrysler Concordes went from 0 to 60 in 8.7 seconds. Okay. Now, compare this scenario to the tax refund, right? Is 8.7 more than 8? Yes, right? But in this case, is more time better or worse? So if we think of the tax refund, right, is it better to get more money back or less money back? And right, everybody's happy with more money, right? So in the tax refund scenario, we had a problem whenever the money was less than 1,000, right? But if it's more than 1,000, no one's gonna tell on you, right? All right. So the point I'm trying to make is 8.7 seconds is worse than 8 seconds. Because if the engine is better, that means it can go to 0 to 60 in a less amount of time. It can get there faster. So when Consumer Reports magazine did their test, they tested 10 cars, and it took them 8.7 seconds, an average of 8.7 seconds to go from 0 to 60. So what's the original claim? What's the claim from the company? Chrysler claims 8 seconds, right? So this is going to be my null hypothesis, my original. This is the company hypothesis. And then the alternate is, after we took a sample and we tested this claim, this is going to help us with HA. Right, and we have to answer, is 8.7 more than 8 or less than 8? So I'm going to use black for this one. Okay, so I'm going to do HO, and the parameter of interest, usually referred to as mu, equals 8 seconds, right? And then HA. Okay, when they sampled the 10 cars, did they get a result that was, how does it compare to 8? In this alternate assumption or hypothesis, did they get a value bigger than 8 or less than 8? And they got a value larger than 8. Okay, so this is my null hypothesis, and this is my alternate. Okay, so let's try it again with the second example, the Kmart. Again, we're not done with number 1, but I just want to find the hypotheses. Okay, so let's go to number 2. Let's find the hypotheses for number 2. Kmart brand 60-watt light bulbs state on the package that the average life of those light bulbs is 1,000 hours, with a standard deviation of 65. An apartment association complained that the claim was too high. Their sample of 20 light bulbs had a life of only 982 hours. Okay, so here we ask ourselves, when you buy a product, do you want it to last more hours or less hours? Is there an issue if it's more or less? And for me, if I buy something and it says it's going to last a certain length of time, it's going to last 1,000 hours, and it lasts less than that, I'm going to be disappointed, right? If it lasts more than 1,000 hours, then I count myself lucky and I say, oh, awesome. I got a really good light bulb that lasted more than the expected time, right? Okay, so let's break down the hypotheses then. So we're looking at the average life of the light bulb. So the company, Kmart, is, or whatever package it came from, maybe General Electric, is claiming that their light bulbs last 1,000 hours. Now, an apartment association thought that average was too high. They think that the company is lying, right? So they took 20 light bulbs and put them to the test, and they found that they got an average of 982. So my hypothesis, my null hypothesis, is that the average lifespan of the light bulb is 1,000 hours, right? But the alternative is when they put it to the test, how did it compare to 1,000? How does 982 compare to 1,000? Is it more than 1,000 or less than? It's less than, right? So this is my null hypothesis, and this second one is my alternate hypothesis. Okay. Let's do one more. Practice, right? Tennis balls produced by a particular machine are supposed to achieve the design specification of 3 inches with a standard deviation of 0.2. A large USTA tournament thinks the tennis balls are too large. Their sample of 40 balls resulted in average of 3.1 inches. So this is probably the average, diameter of the tennis ball, right? And so if we want to identify the hypotheses, the 3 inches is from the machine that produces it, right? Because it was designed to a specific specification. And the alternate is that when the USTA put it to the test, they got a value that was larger. So that gives us two hypotheses. Either the average diameter is 3 inches, but the alternative, when we compare it to 3 inches, the alternative was 3.1, which is greater than 3 inches. Okay, that's part of it done, right? And so just to check our answers, we have on this slide to check ourselves to see if we made the correct hypotheses, right? Now, it did say to also check, to do to draw a distribution and check the probability, right? So let's do a couple. Let's do the Chrysler one. Okay, so if we go back to the Chrysler, that was talking about the cars and how fast it takes them to reach 60 miles per hour, right? And so from the sample, they got some cars, and it was from 10 cars, and they've got an average time of 8.7 seconds, minus Chrysler's claim of 8 seconds, divided by the standard deviation of 1 over the square root of 10. Now, what I'm going to correct here is this symbol here, where the Z formula is, should be a sigma. Okay. So calculating this fraction gives us 2.21. We go to the Z table and we look for 2.21. Let me use red. Okay. So 2.21 brings me to this percentage. 0.9864. But remember, the normal table shades everything below. But what was the hypothesis? What was the claim of the hypothesis? Did we say that HA is greater or less than? Is 8.7 greater than 8 or less than 8? It was greater than 8, right? So what I'm going to do is actually subtract here. 1 minus what was the number? 0.9864. Which gives me 0.0134. Okay. And then let's look at the, oh, sorry, I didn't talk about the diagram, but the diagram has the average at 8 seconds, and then we go down 3 and up 3. And then 8.7 is about here, and so we're shading everything above this, and so this shaded area is 0.0134. This is kind of going back to sampling distributions. Okay, if we get the Kmart example, that was the light bulb example, our sample X bar, when we tested 20 light bulbs, gave us an average time span of 982 hours. minus the claim of 1,000 over the standard deviation. So again, instead of S, it should be sigma. 65 was given in the text, and so we calculate this fraction and it gives us negative 1.24. So if I go to the Z formula, I'm looking for negative 1.24. Negative 1.24, which brings me to this value. Okay. Negative 1.24 gives me 1075. So this is 10.1075. This is from the table, this is from the calculator, however you choose to get it. Okay, and then we have the distribution here, where the mean, the average time of the lifespan of the light bulb is 1,000. Then we're adding and subtracting, not 65, but 65 over the square root of 20. And then we look for where 982 is. It's around here, right? And we're going to shade everything below that. And again, why are we shading below? Well, we got to ask ourselves, is 982, how does it compare to the 1,000? How does 982 compare to 1,000? It's less than, so we're going to shade everything less than. Okay? So the next thing I want to talk about is how do we phrase our hypotheses? Okay? Again, this is kind of a longer video than the other ones will be because I'm explaining this topic for the first time. So I'm kind of breaking everything down. But at the end, when we make our conclusion, it has to be based on the hypothesis that we wrote down and we stated, and the probability that we calculated. Okay, so for this topic, again, I always like to use the justice system. Right? If we are making a decision on someone that's accused of a crime, we have to tell ourselves, okay, what is our hypothesis? We have to make one of two choices. Either we believe that the defendant is innocent. That's our default hypothesis, right? Because our system says innocent until proven guilty. So we believe he's innocent, but if we find evidence that contradicts this, then we believe the alternate hypothesis that he's guilty. But we need to find evidence first, right? So in our case for statistics, the evidence is the math, the calculation. What did we get from the calculation? Is that enough evidence to prove the alternate hypothesis, or is it weak evidence and we stick with the original hypothesis? Okay. What does the jury state if the defendant wins, right? He says, not guilty. Right? We hereby find the defendant not guilty. They don't say we hereby find the defendant innocent, because they're trying to find evidence, right? If they don't find enough evidence, then we can say, oh, for sure we know he's not guilty, but we don't know if he's completely innocent. Maybe he had a good alibi, but he was still involved somehow. We just couldn't pin it on him, right? So, but I don't want to go on a tangent here. I just want to make sure we understand and are clear that the HO is the original hypothesis, but if we have evidence to contradict it, then we go with the alternate hypothesis. Okay? And on this next slide, let's see, what did I put here? Yeah, so here I put kind of a template, okay? Try to color code here. So if we have evidence that the criminal or that the defendant is guilty, then we reject the original hypothesis because we have evidence to believe the alternate hypothesis. We reject the original hypothesis because we have evidence to believe the alternate hypothesis. So that's one scenario. What about the opposite? What if we don't have enough evidence to convict? Okay, so then we're going to state kind of keeping them in the same order, but I'm just changing my sentence. So instead of saying we reject, I'm going to say we failed to reject the belief that the defendant is innocent because we do not have the evidence to believe he is guilty. Okay? And we're going to keep doing this as we work on problems, and I think it just takes time to kind of build a pattern of it. But this is basically it. It's either if we have evidence to contradict the original, then we say we're going to reject the original because we have evidence to believe the alternate. If we don't have evidence, then we say, okay, we're going to keep believing the original because we don't have evidence to believe the alternate. So either you have evidence or you don't. And we're going to keep practicing this wording. But let me move on. All right, so now going back to the poem. And you're probably thinking, oh, I thought we were done with this one. No, there was a couple of steps we needed to do. We needed to find the hypothesis, the original and the alternate. Then we did some calculation. Remember we drew the normal diagram? Yeah, so if we would go back, remember we did found a z-value, and that z-value gave us a probability in the table, which was this one. And so based on this probability is 1%, right? 0.01 is 1%. So is a 1% probability very likely or very unlikely? And you should be correct in saying it's very unlikely, right? So what that means is when the Consumer Report put 10 cars to the test and they got an average of 8.7, that 8.7 was a rare occurrence. How rare? There's a 1% chance of happening. So that means that Chrysler's claim, this was Chrysler's claim. Chrysler's claim. They're claiming 8 seconds, but our sample showed 8.7 seconds, which had a 1% chance of happening. So there's something fishy going on, in other words. Because we got a value that was so far from the claim, then we're going to reject the original claim since the probability is so small. There's enough evidence to believe that the mean concord time is greater than 8 seconds. Okay, so here in this first part we're saying what's going to happen to the original claim. We're going to reject it, right? Why are we rejecting it? Because when we did the calculation, we got a probability that was so small it's very unlikely of happening. So I'm going to say there's enough evidence to believe what? To believe the alternate. There's enough evidence to believe that the average concord time is greater than 8 seconds. Okay, so our decision basically is based on the probability that we get. If the probability is really small, then this is the steps we're going to take. We're going to reject the original and believe the alternate. Now, what's the opposite of this? If the probability is large, then we do the opposite. Okay. And an example of that is in the Kmart example. So that's why I put that slide on there. So let's go through it again just in steps. Okay, so this is the claim of Kmart. Okay. Then some people put it to the test. Some people put the claim to the test and they got not 1,000 hours but 982. And so when we did our calculations, we got a probability of 10%. And since that probability was not very small, then I'm going to do the opposite of what I did with the Chrysler. I'm going to fail to reject the original, meaning I'm going to keep believing the original claim. And because the probability was so small, that means there's not enough evidence to believe the alternate. Okay. And what's the alternate claim? That the mean lifetime is less than 1,000 hours. Okay. Now to the part that I've wanted to come to from the beginning. Let's look at the acronym. This acronym, I think it's in one of the pages that I gave you at the beginning of confidence intervals. I gave you a page that gave the acronym of panic, and on that same page it gave the acronym of phantoms. So part of the acronym of panic is in phantoms. Okay, there's a P, there's an A, there's an N. So then what's new to the acronym? Let me highlight those in blue, okay? So the new steps are the following. Okay? And in a way, I want to say, these two are kind of done at the same time, and these two are done at the same time. But just to spell out a word, right, we use the acronym phantoms. So I want to say, there's three changes, or three additions, I should say, to panic. There's hypothesis, there's calculations. Let me go ahead and write that in. So this is kind of the calculation part. And then the last two letters of the acronym are the kind of the conclusion part. Okay, so there's hypothesis, there's calculations, and there's conclusions. But we're still going to be doing P, A, and N of panic. Okay, so let's go to an example. So you can put this all together. Right. So this is the first problem on your third page. It says, a package delivery service claims it takes an average of 24 hours to send a package from New York to San Francisco. Okay, so that is the claim. So let's start off with that. Let's make a note of that. That's HO. That's the original hypothesis or claim from the company, right? An independent consumer agency is doing a study to test the truth of this claim. Several complaints have led the agency to suspect that the delivery time is longer than 24 hours. All right. So right there. Longer than 24 hours. So that tells us right there that they believe that it takes longer. So that's going to be our alternate hypothesis. I'm going to call it HA. Okay, we continue reading. It says, assume that the delivery times are normally distributed with a standard deviation. Assume sigma for now of 2 hours. Okay, with a standard deviation of 2 hours. A random sample of 25 packages was taken. And I don't know why it doesn't have it here, but it should say the mean delivery time. The mean delivery time was found. Let me zoom out here. The mean delivery time was found to be 24.85 hours. Okay. What else? Okay. So this is the situation. Okay, a delivery service claims that they can get your package in 24 hours, but because of complaints that have been brought up, there's a consumer agency that put this claim to the test. They mailed off 25 packages, and they got an average delivery time of 24.85 hours. All right. So if we continue to look on the slides, we see that we're still going to state the parameter. Okay, so the parameter in this case is, we use a symbol for mean, this mu symbol. It's the average delivery time. The average delivery time. The original claim, the original hypothesis is the company's claim. Company claim here. But when the consumer group put that to the test, they got a delivery time that was more than 24 hours. So this is what the agency tested, because they believe that they take longer than 24 hours, right? Okay. Step A of phantoms is like the step A that we've seen before. Was the sample of 25 packages, was it random? Right. How many did they sample? It was 25. This is kind of a side note for me. So were these 25 packages sampled randomly? Yes, I think it said in the problem. It also said in the problem that the distribution was normal. If you go back and read it. And then condition number 3. It's safe to infer that there's a population of at least 250 packages for independence. And again, How did we get 250? You just multiply 10 times n. But n was 25, right? So 10 times 25 is 250. All right, n, like in panic. For now, we're going to call it a test of significance. That's the name of the procedure that we're conducting. We're doing a test of significance. All right. So let's go to the next letter in the acronym. That letter is T, which stands for find the test statistic. In this case, find the z-value. Okay, so this is the calculation part, if you want to think of it that way. So I know on this video it kind of put everything there, but if you go on the slide on Blackboard, it displays it in steps. Okay, so this is the claim of the company. It's 24 hours. The standard deviation in the scenario said it was a standard deviation of 2 divided by the square root of n, which gives me 0.4. So let me just write it again. It's going to be sigma divided by the square root of n. That's this part here. Okay, I just want to identify it so that we know what it is. This is given in the text. This is also given in the text, sample size and sigma. But if I divide these two, I get 2 over 5, which is 0.4. Okay. So if I add 0.4, this is my mean of 24. If I add 0.4, it's 0.4, 0.8, 25.2. And if I subtract, I get these. Now, when they sampled 25 packages to deliver, they got a sample average of 24.85. So we plug it into this Z formula. Okay. Plug it in. But remember, we just calculated this. This is 0.4, so this is my denominator. X bar is 24.85 minus mu, which is 24. Okay. Calculating this fraction gives us 2.125. Okay. And that's what I want to get. That's what I want to put in the next step of my acronym. Okay. So everything that I wrote here, I'm going to write it in my acronym. Everything I wrote in green. Okay. This is step T. Let me go to the next slide and you'll see that step there. So this is what I got from my calculations. I got 2.125. Then I have my Z chart here, 2.125. Let's round it up to 2.13, right? .13. So that gives me 0.9834. 0.9834. But I'm going to subtract from 1 because I don't want less than, I want more than. How do I know that I want more than? Well, we can always look back at the alternate hypothesis, right? It says more than 24. So I'm going to shade more than. Anytime I want to find the probability of more than, I do 1 minus. Okay. Now, one thing that I had mentioned before is this alpha. And what I had said before was alpha was going to be the level of significance. Okay. And having that level, it's kind of my comparison value. By default, my level of significance is 5%, unless it's stated in the problem what the level was going to be. Okay, like in number 3 on your assignment. For number 3, if you read number 3 on the last page of the handout, you'll see that at the very end of the scenario, it says use a level of significance of 3%. Okay, but this 5% on my PowerPoint slide, 5% is the default. Default. Unless they tell us something different in the text. Okay. Now, what we're going to do is we're going to compare, because 5% is my comparison value. Now, if I compare it to the probability that I got, is 0.01 bigger or smaller than 0.05? It's definitely smaller, right? So that leads me to my so that leads me to my conclusion. And my conclusion is based on this fact. What was my p-value? It was 0.0166 from here, right? Is that value less than or greater than 0.05, which is my level of significance? It's less than, right? So if it's less than, then we're going to reject the original hypothesis. So why are we rejecting it? Because our p-value is less than alpha. Meaning that the 24.85 that they got was very rare. It was very rare that they got a delivery time that was longer than 24 hours. So if it's very rare, that means that 24 hours is not the average. The average is probably closer to 25 hours. Okay. But since our p-value is less than 0.05, we're going to reject the original claim because there's not enough evidence to believe the alternate claim. HA. Okay. So let me summarize it one more time. So our parameter was we were interested in the true average delivery time of packages. The company claims that they take 24 hours. But we want to put that to the test, or an agency put that to the test. And they got an average that was more than 24 hours. They got 24.85. So after we check these conditions, we do the calculations, right? And so we calculated the z-value. Again, what's the formula for the z-value? Just to write it out. You guys can write it out also. This is my formula. Plugging everything in, I get 2.125 as my z-value. I look for that value in the table, and it gives me 0.9834. But I'm going to subtract from 1 because I want to get greater than. Remember, the table only shades less than, so 1 minus will give me greater than. And that gives me a probability of 0.001, 1.6%. Now, this value is less than 0.05, so that tells us what we should conclude at the end. Our conclusion should be that we reject the original claim. Why? Because this p-value is too small. And because this p-value is small, there is enough evidence to believe the alternate. What was the alternate hypothesis? That they do take longer than 24 hours. All right, and the last thing I want to go over is just how to reword the conclusion just one more time. Right, so I kind of put this last slide there as a template. Okay, and so there's two conclusions I can make. If I believe the statistic is just too extreme and unusual, then I will reject the null hypothesis. If I believe the statistic is just a normal chance variation, I will fail to reject the null hypothesis. Okay. So I have this general template statement that we're going to follow. Okay. And I'm going to follow the red path if my p-value is less than alpha. And I'm going to follow this blue path if the opposite is true. Okay. So if my p-value is less than alpha, I'm going to reject HO. Why? Because the p-value is less than alpha. That means that there is enough evidence to believe HA, and then you state whatever HA states. Now, the second conclusion is the blue path. We fail to reject HO since the p-value is greater than alpha. So if you get a p-value that's greater than the level of significance, then I'm going to say there is not enough evidence to believe HA, and then you state HA. Whatever that may be. Okay, so I hope this video explains a couple of things and clarifies some things. If not, again, if you guys want to request, we can hold another session, or I can answer better details and clarify some things that you guys still might have trouble with. I'm open to do that again. So yeah, just message me on Remind if you guys want to have another Zoom session. But other than that, thank you for joining me again. Hope you have a great day and stay safe.